Hello everyone, today we'll be discussing about cryptographic and security mechanisms for secure end-to-end group communication in instant messaging applications. The motivation for the security in group communication is that in recent times, end-to-end communication between two parties is rather well researched as compared to end-to-end group communication among multiple parties. So the group communication needs to meet the user experience expected from an instant messaging application platform. The objective is to understand the challenges in security of group communication and their corresponding solutions. We will see some new security definitions and how these definitions map to group communication mechanisms. You may think that why can't we simply reuse the existing two-party communication strategies for group communication also? It seems easy to use strategies for communication between two parties for group communication also. Like a member can establish a point-to-point session with each group member. But the problem is, as the size of the group increases, the overall computation cost of sending messages will also increase linearly. And the metadata associated with a group keeps changing. So we need some protocols for efficient group communication without any message leakage. Consider the following example where a group of people communicate in an isolated room. These are the properties which are unique to the group communication, like traceable delivery, authenticity, no duplication, no creation, confidentiality, and closeness. We will see some few security terms now. So what is forward secrecy? Forward secrecy is the property that ensures that a session key derived from a long-term public and private key will not be compromised if one of the private keys is compromised in the future. Basically, it protects past communication by protecting the past session keys, and this is achieved by generating new session keys for each message. Diffie-Hellman key exchange is a cryptographic protocol that provides forward secrecy. Consider the following example where Alice and Bob will agree on a session key using a key exchange algorithm such as Diffie-Hellman algorithm. There will be a new session key for every message sent. What is future secrecy? This property guarantees that encrypted messages in a session remain secure even if the previous session key was compromised. It is also known as post-compromise security because the property ensures confidentiality of future messages after a compromise. So even if at some point the long-term secret together with the party's current session key and all other secret states are corrupted, the future messages can still be secure. Signal is an example that achieves future secrecy with the double ratchet algorithm. Double ratchet algorithm is a key management algorithm that can be used as a part of cryptographic protocol to provide end-to-end encryption for instant messaging. It provides forward secrecy and post-compromise security by ensuring that the communication party generates new keys for each message. Now, Khalid will take over for the further slides.
Thank you, Vinay. Now, in the double ratchet algorithm, the way the future secrecy and forward secrecy are achieved is because of these KDF functions. And these KDF functions, these key derivation functions, are nothing but pseudo-random functions which produce a random output given an input and a KDF key. And as you can see here, the output of one function is being mapped as an input to the next function, forming chains of KDF functions. And behind the scenes, keyed HMAC based on SHA-256 is being used here. Now, in the double ratchet algorithm, if you consider Alice and Bob in this communication setting, there will be three ratchets. These gears are called ratchets, where every time they produce new keys. And the important thing to note is that the sending and the receiving keys need to be in sync. This is the Diffie-Hellman ratchet, which we'll come to later. Now, in the previous example, we saw these sending and receiving ratchets. These are this is where the symmetry key ratchets work, and each of these ratchets have a chain of KDF functions, The chain key is used, and the chain key is used as fed as input to this KDF function, producing two outputs, chain key and message key. And this message key is used for each message that is being sent or received. Notice that this message key is not related to generating the next chain key or the next message key. Over here, as you can see, AES is being used. Now, it is the responsibility of these ratchets to ensure that each encryption key is a new encryption key is being used for each message that is being sent or received. So far, if you observe the previous diagrams, we have seen that the message keys are unique. But what about these chain keys? These chain keys are still not unique. So that's where Diffie-Hellman ratchet comes, and if it basically produces new chain keys also. So not only are we making new message keys, we are also generating new chain keys, and this is based on the elliptic curve Diffie-Hellman protocol. How does this work? It's basically Alice takes Bob's public key and her private key, generating a DH output. This DH output is same as the DH output which Bob can generate, taking Alice's public key and his private key to generate this, to perform this exchange of chain keys. And when, if you see, if you, this entire diagram is for Alice, and if you can see that in her root key, she is using a different receiving chain key for her receiving ratchet and a different sending chain key for a sending ratchet. Now, in this algorithm, again, as I said before, there are three ratchets. Even though the name says double, but there are actually three ratchets behind that are used. And you can see that this ratchet, right, this ratchet over here, Diffie-Hellman ratchet, feeds different chain keys to the sending ratchet, receiving ratchet. Same thing on Bob's end. And these chain keys, these ratchets, they produce different message keys. So there are two keys, message keys and chain keys. Now, how does this all tie up? This is all of these terms which we've seen so far are used in the signal protocol, which uses the double ratchet algorithm. It can be used, and it also supports end-to-end encrypted group chats. Now, the signal application is an open source implementation of this protocol. WhatsApp also claims to use this protocol for key exchange, but does not use it for its group communications. Now, just a brief overview of how Signal app handles group messaging. In each group in Signal has a unique 128-bit vector ID, and the group messages are treated the same way as a direct message. The only difference is that the group message has this group ID attached to it. And whenever a member sends a message to a group, to his or her group, that a timestamp is also used along with the group ID, and each message is then encrypted for every other member of the group. And all of these encrypted ciphertexts are then sent by the server to the recipients. And similarly, even in the group management for Signal, again, whenever a member is added to a group, the modifying member sends an encrypted message containing the new set of members to each other member. Then each member updates his or her group list. And that's how the group management is done. And in the legacy group version, which also has an attack and which is vulnerable to attacks, basically every member used to have admin access, and no member can be removed by any other member. Pros and cons. Biggest pro is a self-healing property of ensuring future secrecy. This is because, of course, you will have new chain keys and new message keys. Very recent design, and it's already in use by the popular messaging applications. Cons: vulnerable to side channel attacks. Of course, screenshots, keyloggers, they can be taken. Ability to reset the state and or support out of order encryptions, decryption is quite complex because of handling three different ratchets. And the protocol itself is implemented differently in different apps. Now, this is an example of a flaw in how Signal implemented its legacy group features using the Signal protocol. And this attack basically just requires two things. The attacker needs to know the unique group ID of the group and the phone number of any group. And these two are relatively easy to figure out, especially if the attacker was already an existing member. The attacker just needs to send a modified message directly one-to-one to a known member's phone number. and the modified message should just have a group update message. After receiving the message, Alice updates her group list by adding the attacker in her personal group list. Now, since Alice's group list includes the attacker, future messages which Alice sends to the group will also be received by the attacker. And not only this, if Alice were to send the group update message to the group, each member of the group will update his or her own list, and in each one of them, each one of theirs group list will have the attacker. Now, whichever messages the group members send, all of them would be received by the attacker. And it's a very serious flaw. And this legacy group feature is now still there, but the Signal has now updated its group features. Again, this flaw violates the following properties: no creation, additive closeness, future secrecy. You might be wondering what these terms are, and in the context of secure end-to-end communication, many such new terms arise, and security models are built on these terms, and then they are evaluated. And as you can see, in the context of group management, like this is basically not just for communication. These are group-related functions that get violated. So this is all for our presentation. Thank you for your patience, and if you have any questions, you can reach out to us.